Hi, in this video I'm going to go over the analysis of this buck-boost converter shown here. And for this switch mode power converter, we have that the output voltage VO can be either larger than or smaller than the input voltage VS. Now to analyze the circuit, we're going to make some assumptions. They're as follows. First, we're going to assume that the switch is turned on during the DT interval, and then we're going to open the switch during the 1 minus DT interval. So in the DT interval, we have the switch closed, and then in the 1 minus DT interval, we have the switch opened. The second assumption we're going to make is that this circuit is operating in periodic steady state. This means that the inductor current at the beginning and end of the period are equal. And this is equivalent to the statement that the average inductor voltage over a period is equal to 0. And this is called inductor volt-second balance. For the capacitor, we're going to have the capacitor voltage being equal at the beginning and end of a period. So that's equivalent to the capacitor current averaged over a period equal to 0. And this is known as the capacitor charge balance principle. The third assumption we're going to make is that the inductor current is continuous, so that we're operating in the continuous conduction mode. This means that the inductor current IL of t is greater than 0 for all t. The fourth assumption we're going to make is on the capacitor, and that's we're going to assume this capacitor C is large enough such that the output voltage is a constant DC value. So this is called the small ripple approximation on the capacitor voltage. This is where we assume the output voltage ripple, the ripple on the capacitor is negligible and we can ignore it. Now we will relax this assumption when we want to study the output voltage ripple later on. The last assumption we're going to make is that we're using ideal components. And this just means that the input power supplied by the source voltage Vs is equal to the output power delivered to the load resistor. So to start our analysis, we want to examine the inductor voltage during the DT interval and during the d'T interval. So let's start by drawing the circuit in the DT interval. So in the DT interval, the switch is closed. So we're going to have a short circuit in place of the switch. And here we have the inductor, and the diode will be reverse biased. So it's represented by an open circuit, and then we have the capacitor and resistor. Now in this interval, we see that the inductor voltage is equal to the source voltage Vs. Now what about the d'T interval? So in the 1 minus dt interval, we're going to open the switch. So the switch is an open circuit. So the diode is going to become forward biased in this state. And we once again have the capacitor and resistor at the output. And the reason that the diode becomes forward biased is because you can see in this DT interval, we have the inductor current flowing like so. However, because the inductor current cannot abruptly change, it needs to continue to flow in the d'T interval. So this means that the diode is going to conduct to provide a path for the inductor current to continue flowing in the d prime t interval when the switch becomes opened. So in this d prime t interval, we have the inductor voltage VL. It's going to equal the output voltage VO. So now we found the inductor voltages in both intervals, and we can apply the principle of inductor volt-second balance, which we had said was the average inductor voltage over a period is equal to 0. Now, the average inductor voltage is also expressed as, during the dt interval, we have the voltage as Vs, and then during the d prime t interval, we have the voltage as VO. So now we've derived the equation for the inductor volt-second balance, and we can use this equation to solve for the voltage conversion ratio. So VO over Vs is the quantity that we desire. So we can move dVs to the left side, and we have 1 minus dVo on the right side. And now we're looking for VO over Vs. So if we divide both sides by Vs and as well as 1 minus d, we get that the conversion ratio is negative d over 1 minus d. So we can note, first of all, that because the duty cycle is always between 1 and 0, that this quantity circled here is always positive. So this negative sign indicates that the output voltage has a polarity reversal compared to the input voltage. So the output voltage will be negative. Now, the other thing to note is that if we have a duty cycle greater than 0.5, then d is going to be greater than 0.5, while 1 minus d is going to be less than 0.5. So we're going to have a voltage conversion ratio in which the magnitude of the output, so the magnitude of the output is greater than the magnitude of the input. By the same token, for a duty cycle that's less than 0.5, we're going to have that the magnitude of the output voltage is less than the magnitude of the input voltage. And the magnitude of the input voltage is positive. The input voltage is positive, so we can just ignore those absolute value signs. So this is an important equation here. Now, we can also solve for the duty cycle that we need for a given voltage conversion ratio. So in this equation here, we can isolate d. So we have dVs plus 1 minus dVo equals 0. If we isolate d on this side, we have Vs minus Vo. And then we move the Vo to the right side to get minus Vo. So in this case, the duty cycle d equals negative Vo over Vs minus Vo. Now, negative Vo, we know, is equal to the magnitude of the Vo. So we have the magnitude of the output voltage is equal to negative Vo because the output voltage is a negative quantity. So we can also express this as the absolute value of Vo over Vs plus the absolute value of Vo. So if we desired a given output voltage and a source voltage, we can find the duty cycle that we need to get that desired output. Now, the polarity reversal on the output is a disadvantage in some applications. But you can see that because we have the ability to get both a larger output voltage magnitude and a smaller output voltage magnitude, the buck-boost converter combines the capabilities of both the buck and the boost converters. Another thing to note is that during the dt interval, we have the energy being stored in the inductor. And then during the d prime t interval, that energy is being released to the output load. The one thing to know is that in both intervals, the source voltage is never directly connected to the output voltage. There's always some open circuit in between the source voltage and output voltage. So this means that this buck boost converter is an indirect converter. So now the next step is to figure out what some of the waveforms look like. So let's look at the inductor current waveform. So during the dt interval, we have that the inductor characteristic equation is VL equals L DIL dt. So VL in this interval is equal to Vs. So that means that DIL over dt is equal to Vs over L. Now this quantity Vs over L is just a constant. So this means that it's actually a positive constant, more specifically. So the inductor current is linearly increasing in this interval with slope Vs over L. You can note because it's linearly increasing, we can also express that the change in inductor current in this interval over the time duration of the interval, which is dt, is equal to Vs over L. Likewise, applying the same analysis for the d prime t interval, we have that delta IL in this interval over the time duration, which is d prime t, is equal to VO over L. So this is a negative constant. So that means that during the dt interval, we have the inductor current linearly increasing with slope Vs over L. And then in the d prime t interval, we have the inductor voltage decreasing with slope VO over L. And because we're operating in periodic steady state, this waveform will just repeat continuously. So this matches up with the inductor voltage waveform. So if we were to draw that out, we would have during the dt interval, we have the positive voltage Vs. And then in the d prime t interval, we have that the inductor voltage is the negative value VO. So by inductor volt-second balance, we know that the average inductor voltage is equal to 0 over a period. So that means that this positive area above the time axis is equal to this negative area under the time axis. And this is because of the inductor volt-second balance principle. So the next waveform we want to look at is the diode current. So we can see that the diode current, in this case, in the dt interval, we have that the diode current ID is equal to 0. And then in the d prime t interval, we have that the diode current ID is equal to IL. Now, what about the capacitor current? So the capacitor current is shown here, IC, and we also have the output load current as V out over the load resistance R. So in this interval, the DT interval, because the diode is open circuited, we have that the capacitor current by KCL is just equal to VO over R. Now in the DT interval, the capacitor current is also going to include a component of the diode current. So in this case, by KCL, we see that the capacitor current is going to equal the diode current plus the output current. So in this case, we'll have that the diode current is also equal to the inductor current. So I'm going to make a little room here. So we can just substitute IL for ID. So this is an expression for the capacitor current in the D prime T interval. So to draw out those waveforms, let's start with the diode current. So ID equals 0 in the DT interval, and then it equals IL in the D prime T interval. Now for the capacitor current, we can draw the waveform as well. And in this case, during the DT interval, we have that the capacitor current equals VO over R. And we know that the output voltage is negative, so the capacitor current during this interval will be negative. Now in the D prime T interval, we had found that the capacitor current is the inductor current plus VO over R. So it's going to be equal to IL, but shifted down by VO over R. So these are our waveforms for these voltages and currents. Now, what about the average inductor current? What is big IL or average IL over a period? Well, we can find this by analyzing the output power and the input power. So we know the power absorbed by the load must be the same as the power supplied by the source. So we know the output power PO is equal to VO squared over R. And then the source power is equal to the voltage of the source times the DC current of the source. So we know these two quantities are equal to each other. So to figure out what IL is, we can express the source current in terms of big IL. So we know that during the DT interval, the source current is equal to the inductor current, while for the d prime t interval, the source current just equals 0. So therefore, IS equals IL times D. So we can substitute this expression in for IS. So we get VS times IS, which is ILD. This equals the output power, VO squared over R. Now, if we divide both sides by VS times D, we can solve for the DC component of the inductor current. So big IL is equal to VO squared over VS dr. Now we can further simplify things by using this voltage conversion ratio here. By substituting in VO equals negative D over 1 minus D times VS, we're going to get the following expression. So substituting in negative D over 1 minus D times VS in for VO. The VS's will cancel, so we're left with a VS in the numerator. And then the D squared in the top will cancel out with 1D on the denominator, so we're going to be left with 1D in the numerator. And then we will have 1 minus D squared R. So this is the expression we found for the average inductor current. Now, how about the maximum inductor current and the minimum inductor current? So we can find that by observing the slopes. So we're looking for delta IL here, and delta IL is equal to, during the dt interval, we have the slope as VS over L, and this slope occurs for the time interval dt. So then the swing in the inductor current is Vs times dt over L. So we know the average inductor current is big IL. So therefore we can find that I max equals the average inductor current plus delta IL over 2, and I min is equal to IL, but minus delta IL over 2. And this is because delta IL over 2, we just have two equivalent parts to give us I min here and I max here. So knowing these expressions, we can write the expressions now for I max and I min. So I max is equal to IL plus delta IL over 2. Substituting for IL, we can plug in this expression here. And then delta IL is equal to Vs dt over L. And then we also have that factor of 2. Likewise, the minimum inductor current is the same thing, but we have a minus sign there. Now, the reason that we're looking for the maximum and minimum inductor current is we want to observe the point at which the inductor current remains continuous. So we have the condition that the inductor current is always positive for all t. So that means that the minimum current I min must be greater than 0. So in this case, we can solve this inequality to give us the parameters for the inductance and the switching frequency, in which we will keep the buck-boost converter in the continuous mode. So if we move this over, we have VSD over 1 minus D squared R, moving this over to the right side. And we also see that the VSDs on both sides can cancel. And one more thing is that we can move the T to the denominator, because T equals 1 over F, so we can write F in the denominator instead of T in the numerator. So this implies, if we move LF to the right side, that the inductance times the switching frequency is greater than 1 minus d squared R over 2. So this is the combination of the inductance and the switching frequency in which we maintain continuous current operation. So if we've decided on the switching frequency, then we can simplify by dividing by F on both sides to find the inductance. So if we decided on the switching frequency, this is the condition on the minimum inductance we need for continuous current. This equation is important for the design of the buck-boost converter's inductor. So we've analyzed the circuit under the small ripple approximation for the capacitor voltage. Now, what if we relax that constraint and study what the voltage ripple is at the output? In this case, we know that for a capacitor, we have the equation that the change in charge across a capacitor is equal to the change in charge stored on a capacitor is equal to the capacitance times the change in voltage across the capacitor. In this case, the voltage across the capacitor is the output voltage VO. So in this case, the output voltage, the peak to peak output voltage is equal to delta Q, the change in charge stored on the capacitor, divided by the capacitance. Now, what is delta Q? In this case, delta Q is this current times this time duration. So this is delta Q. And we can find this by looking at the capacitor current waveform. So this area here is the amount of charge that is stored onto the capacitor in the dt interval. So this is just the area of a rectangle, which is V out over R times dt. So we can plug in this expression for the change in charge across the change in charge stored in the capacitor, and this equals V out dt over R, and then we also divide by the capacitance C. And we often look at the ripple ratio, so we divide both sides by VO, and the output voltage ripple ratio is delta VO peak to peak over the output voltage, and that gives us dt over RC. And once again, we can put the period on the numerator as the frequency in the denominator. So therefore, the output voltage ripple ratio is equal to D over FRC. So as with the other converters we've studied, the ESR of the capacitor will also contribute significantly in some cases to the output ripple voltage. So that's when we have some equivalent series resistance with the output capacitor, little rc. In that case, the output ripple voltage due to the ESR is equal to this change in capacitor current times the ESR resistance. Now, the change in capacitor current we can see from this capacitor current waveform. So IL, we see this point is I max plus V naught over R, and the minimum is V naught, I min is V naught over R. So the swing in the capacitor current is equal to I max. Because it's I max plus V naught over R minus V naught over R. So then the swing in capacitor current is just equal to I max, which is the maximum inductor current. So therefore, we can substitute in I max for delta IC. And this is the contribution of the ESR to the output voltage ripple. So overall, this was the analysis of this buck boost converter in the continuous current mode. And it's a converter that reverses the polarity of the output voltage, but it provides the ability to produce an output voltage magnitude that can be either greater than or less than the input voltage Vs. So in essence, it has both the ability to buck down an input voltage as well as to boost up the input voltage. So I hope you found this video helpful in your studies of power electronics. And if you'd like to watch more content like this in the future, please give the video a thumbs up and subscribe to my channel. Thank you.